Okay, great.
Hello, welcome everyone. It's a beautiful day here in Maynooth, and it's a pity we can't be on the campus, but we're going to do this presentation for you now about physics at Maynooth and the various ways you can study physics in various kinds of combinations. What we're going to do here is a double act. You may or may not know that there are two physics departments at Maynooth. There's a Department of Theoretical Physics, which I'm the head of, and there's a Department of Experimental Physics, which Creagh O'Sullivan is head of. And in a moment, I'm going to hand over to Creagh to talk about experimental physics. Then I'll do a presentation about theoretical physics after that, and then we'll have some time for some general sort of questions and so on. But as we start, let me just tell you that if you have any questions as the presentations go on, please use the Q&A little button at the bottom of your screen to type questions in, and we'll try and answer them as we go along. There will be other opportunities to ask questions later, so don't worry about it too much, but it'll be good to have some comments and feedback as we go along. So now I'm going to hand over to Creagh, who's going to talk about experimental physics. She's going to talk to start with about the general science degree and then talk about experimental physics. So Creagh, if you couldn't start now.
Great, thank you very much, Peter. So as Peter said, I'm going to start first by talking about science, or MH201, the CAO code, how you can do physics through the science degree, through that particular entry. And then I'll talk specifically about my own subject, experimental physics, before Peter talks about his. And hopefully that will answer a lot of your questions, but as Peter said, we're more than happy to answer anything that you don't feel we've covered in depth, or if anything occurs to you during the presentation. So I've just got a few slides to remind me what to say, and I'll share those now. So hopefully, can you see a slide there?
Yep.
H201, great. Okay, so there's different ways you can come in and do science in Maynooth, and the traditional way of choosing science would be to choose what we call an undenominator omnibus degree, which means you come in and you say, well, you know you want to do science, you know you want to get a Bachelor of Science, but you don't have to specify from the start what you're going to end up with. You may know exactly what you want to end up with, or you may want to leave your choices open for longer. And the way of doing that is to enter under what we call MH201, our science degree. And that covers lots of different subjects, and you can just see on the slide here the range of subjects that we do that you can finish with if you come in to do science. And we're going to talk specifically today about physics, and there's two physics subjects in the degree: experimental physics and mathematical physics. So I suppose I want to be clear from the start is that if you do science, if you choose science in a university, you're not coming out with general science as such. You will come out with a specialized degree in one or two of these subjects, as specialized as any other degree, but you don't have to specify from the start what your final subject is going to be. So it's a really great option if you like more than one science subject and you're not sure whether you might like to keep both of them, or you're not sure which particular subject is of interest to you. So hopefully if you're at this talk, your interest will be in one or both of the physics subjects. But that's MH201. It's a specialized degree. You will specialize, you will exit with one of these subjects or possibly two, but you don't have to say from the start which one that's going to be. We'll hopefully try and convince you that it should be physics. This is the structure of the MH201 degree, the science degree, and many of our degrees are even our name degrees, where you come in and you've already decided what subject you want to do. They're based on this overall structure. So they're 4-year degrees. If you pick what's called a single honours degree, and you don't have to pick that from the start, you don't have to decide until your 3rd year whether you want to finish with one subject or two. But if you pick single honours, it means you'll finish with one major, one subject. And this slide here shows the overall structure. So in 1st year, you would choose 4 subjects. Then in 2nd year, you do 3, then 2, then 1. So your favorite subject, the one you want to specialize in, you're keeping through all 4 years, and you're dropping a subject per year. Now in 1st year, everybody has to do mathematics. So maths is sort of a fundamental language for science. And really, even if you're doing biology, you'll have to do mathematics in first year. And then you have a choice of 3 other subjects. You might decide in single honours, one of those will be the one you'll decide to keep to the end. So this is the structure. You're dropping a subject every year. One very good thing about coming in to do science under this MH201 umbrella is that when you're in first year and you're doing experimental physics or mathematical physics or biology or chemistry, you're not doing chemistry for physics or mathematics for physics. You're doing mathematics as a mathematician would do it. You're doing chemistry as a chemist would do it. You're doing biology as a biologist would do it. So you can keep any of those subjects as your main subject as you go along. And whichever one you prefer, then that's the one you keep from year to year. But you do end up specialized in one of those subjects. So you don't come out with, say, just general science. You come out with a science degree in experimental physics or in chemistry or in mathematical physics. So that's the structure of our degree. And many of our other degrees are based on that overall structure, that 4-3-2-1 structure. And we call it single honours because you're finishing with one main subject at the end. There's also another option which you can do in Maynooth, and not many other universities allow this. And that's where you keep 2 subjects on. So you'll see here that in your last 2 years, both your last 2 years, you have 2 subjects. We call it a double honours. It's actually what most places would call a joint honours. So it's 50-50 in your last year. And that's very useful if there are 2 subjects and you really like both of them. So again, we hope that you'll choose experimental physics or say mathematical physics. I shouldn't really have put experimental physics here as a main subject. That could be mathematical physics, and your second subject could be mathematical physics and experimental physics. So you could keep both of them if you really, like physics. You could keep both aspects on until your final year. It also allows you to do more unusual combinations. You could pick one of the physics subjects and biology, say. So if you're interested in doing medical physics, for example, this would allow you to keep those 2 subjects on right until the end. So you can do this joint honours structure, and that's a 4-3-2-2 structure. There is an option in second year now where you can take what are called electives or critical skills modules instead of half of one of your science subjects, if you want to get some experience maybe doing a very different topic, the great books, or maybe presentation skills, say, in critical skills. So there are some extra options, which I'm not going to go into in this talk because we're concentrating on physics. But that's the main structure here, I suppose, of the MH201 degree in science. So we hope that you will choose experimental physics or mathematical physics as your degree subject there. And so that's one way of coming in to do a science degree. So you don't have to, when you're coming in, you don't have to say what your final subject is going to be. You may well know, but you don't have to specify it. You can see how you get on, and you only make the decision at the end of each year which subject to keep on. So a very flexible degree, but you will end up as specialized as any other degree. So now I'm going to talk specifically about the subjects that are offered in the Department of Experimental Physics. And that's a degree in experimental physics, or a joint honours with experimental physics and another subject. And also what we call a denominated degree, a degree where you say from the start what you're going to end up with, and that's physics with astrophysics. So it follows our single honours, the single honours structure in MH201. So if you would like to specialise in experimental physics, in the end, you would take experimental physics as one of your subjects every year, and you will end up doing experimental physics only in your final year. Of course, because there's overlap or a lot of common interest in experimental physics and mathematical physics, we allow some optional modules, and you can choose to take those in mathematical physics as well. So there's quite a bit of flexibility there. You would have to take mathematics in first year, and we would recommend you would keep on mathematics or mathematical physics, or both of them, for as long as you can, because it's very helpful for experimental physics. So this is, if you wanted to specialize in experimental physics, at the end, you come in under the MH201 umbrella. So you may know from the start that's what you want to do. You may, if you haven't even done physics in school, you can still do experimental physics in first year, and you may realize that actually, I really do like it and I want to keep it on. So nice flexible structure, and you don't have to make the decision straight away. But that's how you do experimental physics. Now there's another degree option called physics with astrophysics, and here you have decided from the start that that's what you're going to end up with. The reason we do that is because we may not be able to take 100 astrophysicists. So for a university to manage numbers, they often name some degrees from the very start. Physics, we would love to have the problem of hundreds of students beating our door down to specialize in physics. We've never turned away a physics student, I should say that. So coming in the MH201 umbrella won't limit your choices later on as far as physics is concerned. So if you come in to do physics astrophysics, that's a separate entry, MH204. There you've said from the start, it's physics or astrophysics I want to specialize in. And again, it's the 4-3-2-1 structure. So you keep physics and astrophysics as your subject for all years. And within physics and astrophysics, over the 4 years, I would say it's about 2/3 standard physics and 1/3 specialized astrophysics modules. So you'd have a lot of commonality with the experimental physics students, but there will be some modules that will be different, particularly in your 3rd and your 4th years. So that's the physics or astrophysics degree. If you like the joint honors option, this is what you would do. So you would keep experimental physics as one of your subjects all 4 years, and you keep second subject as well. Astrophysics is a single honors degree, if you like. There's no option of doing astrophysics with biology, say, because you have to do standard core physics as well as the astrophysics. So if you want to do a joint honors, the option there is experimental physics and another of the science subjects. So again, just to mention, because a lot of students have the question, should I come in with a named degree or science? And is there a problem if you do science? Is it less specialized or does it look different? And I will say no. Either way, whether you come in under the MH201 umbrella and choose one of the physics subjects as your final subject, or whether you know from the start that you want to do one of these named degrees, either way, you're exiting with a BSc, an honors science degree in experimental physics or physics with astrophysics. So really, it's your choice whether you know from the start what you want to do. You might like the flexibility of the science degree that will keep your options open. But I will emphasize that you're equally specialized no matter which route you choose. By the time you finish, you are specialized. And our degrees are accredited by what's called the Institute of Physics. That's a professional body of physics. And they make sure you've done the core physics areas. Either experimental physics or physics astrophysics will cover those core areas. So either way, you're qualified to work as a physicist, really, in any area, any industry. So if you do physics astrophysics, it doesn't mean you have to be an astronomer. We think it's a really great way of learning physics by doing astrophysics. But it's important to emphasize that you are a physicist. My last PhD student last month has gone into Intel. They're great employers at the minute. They don't mind that he's done astrophysics or physics. They know he's done good stuff. He's a good problem solver, good mathematical ability. He can understand physics. So there's no worries. Don't worry later on, jobs wise. Are you shutting off doors by choosing one option or another? You're not. This is what a first year might look like if you choose any of these subjects. If you do science, you are doing 4 subjects in first year, remember. So each of those subjects would have about 3 lecture hours, 1 tutorial hour where a tutor will help you work through mathematical problems. And because we're doing experimental physics, we do the theory of physics, of course, but we're always bearing in mind that our theory should be testable, and we consider lab work important. So you'd have a 2-hour lab every week. So they're the kind of hours, 6-ish teaching hours per subject, and you have 4 subjects. But of course, you'll be at university, so there's a lot of self-directed study as well. We're reliant on national health advice next year to know what to do with COVID. So this year our lectures and tutorials were online. But we did try very hard to bring students on campus for labs, which we were allowed to do in the first semester. We brought students in for their labs, and I think our students appreciated that. They get to see their classmates. And we brought them in once every fortnight rather than once every week, because we had to spread students out more. So we will try our very best next year to have students on campus as much as we're allowed. And we worked very hard last year to put on laboratories in a very safe way. We had no outbreaks or no problems that way. But of course, we're waiting on advice for next year. So what you do if you study experimental physics, I think the naming can sometimes be confusing. Experimental physics is like the physics you do in school. So it'll be the closest subject to the physics, if any of you are taking physics in school. So we do the whole range of topics. Some of them will be familiar to you from school. Some of them might be new. We might do things like environmental physics, maybe haven't done so much of in school. We do a lot of astrophysics because that's an interest to ourselves here in Maynooth. But you can see from the range there that we cover the topics you would expect if you've done physics in school. Exciting areas from the very small to the very large. So some of the things you will cover your everyday experience, but where things get really weird is where things are much smaller and much bigger than we're used to every day. A whole world opens up to you if you do physics. And I think that you would otherwise be ignorant of. And I think it's a really great opportunity to see all the weird and wonderful things in the universe. So you study this whole range of subjects, but as an experimental physicist, you'd also be thinking about how you test those in the laboratory. And all our experimental physics degrees and our astrophysics degrees are accredited by the Institute of Physics. So you do all the core areas of physics that would be expected of any physicist. If you want to go into, say, secondary school teaching, you would be able to teach physics in secondary school. You'd have to do the teaching qualification, the teaching bit, but you'd be qualified to teach physics in secondary schools. Of course, as well as doing labs and lectures, the further on you go, we bring students on field trips. Well, actually right from first year, but you'll be doing more projects. The further on you go, you get a chance to work with staff in their research laboratories. So in Maynooth, we consider research also very important. And as well as undergraduate degrees, we both departments do have masters, research masters and PhDs. And you can work with those groups as you go on in your career, in your studies. And you can do projects. We bring students on field trips to maybe observatories in Ireland and abroad. We also have gone to hospitals, say medical physics departments in hospitals, Intel and so on, just to give you a bit of experience as to how physics can be used in the field. Just to mention something about astrophysics, I suppose that's possibly most different. Even if you're doing physics in school, you possibly haven't done too much astrophysics. Astrophysics it's a physics topic, so it's about 2/3 standard physics. It's not all about pretty pictures, a lot of meaty physics in it. Astrophysics tries to understand the objects in the universe, it tries to understand the dynamics of the universe itself. We're making measurements of ever more distant and ever fainter objects, and you can't buy instruments off the shelf to do that. So astrophysicists would develop the technology they need and design and build scientific instruments. And we also, as observationists in the experiment, because we're in the experimental physics department, we would also look into making observations of the astronomical objects that we are studying. But I suppose I should emphasize that it's a physics degree. You cover all the core areas of physics, and you don't have to be an astrophysicist after. You can be a physicist in any other area. And many of our students have to bring along some nice pictures if you're talking about astrophysics. We deal with objects from the nearby, from planets. Saturn, I suppose, the poster boy there of planets in our own solar system. But it's a very exciting time in planetary science now, of course, because we're discovering planets around other stars. And we're all very interested in the idea or the question of whether there's life on these planets. So what are they like? Can we find planets that are like the Earth? And there's a group in Maynooth who does research into star and planet formation. So we can now test our theories, not only on our own solar system, but on planets around other stars. We're interested in how stars are born. So they're born in these big gas clouds, like the Orion Nebula, maybe some of you recognize in the center of the slide there. We're interested in how stars form. We're interested in the sun, our own star, of course, in the bottom left of the image there, because it has a lot of impact on how we live on Earth. And of course, now things like climate change and solar energy, it's very important to understand the sun, solar weather. We want to understand how stars like our sun live, how they generate energy. They're basically big nuclear furnaces, if you like, making energy from hydrogen. They don't have fuel to last forever. They will die. We look at how a star dies. In the right of center there, we see what's going to happen to our sun in the future. The core will collapse into a white dwarf, and the outer layers will expand off into space as a planetary nebula. If the sun was bigger, it would explode as a supernova. You can see Eta Carinae about to go supernova in the bottom of the screen, and the famous Crab Nebula in the bottom right there. a supernova explosion. And we study all those things in astrophysics. We also study things at scales larger than stars. The galaxy in the top left there is the Andromeda Galaxy, a neighbor of our own. If you're outside the Milky Way, this is probably what we would see. We look at galaxies that you couldn't pick out with your eyes. So as astronomers, we're not only interested in optical astronomy, but we look at the universe at a whole range of wavelengths. My own particular interest was in radio astronomy. It's what I studied. And on the right, you see radio galaxies. And suddenly when you look at the universe at different wavelengths, you see something very different. We also look at radiation left over after the Big Bang. That's in the center of the picture there, baby picture of the universe, if you like, the picture of the universe when it was very young. And that's a particular research interest of our own in Maynooth. So we worked on a lot of experiments to try and observe the early universe, either from space or from Antarctica is a good place there in the bottom left is an instrument we worked on. So you can see that we look on a whole range of objects in astrophysics, and you need a lot of physics to understand them. So really there's no reason to limit yourself to one small planet in the universe if you're interested in physics. And there's a lot to that. And we think it's important to go visit and try out, get some practical experience. So we take students on field trips. We've been to European Space Agency Technology Center in the Netherlands. We couldn't unfortunately this year, but other years we've taken students to a professional observatory in France to make their own observations, and then they work on the data for their project. And the address there in the center, you might be interested, is a video that one of our students made during the field trip to France 2 years ago. He brought a drone and took some lovely footage of the student field trip. So just to get an idea of what it might be like to go on one of those trips and take data at a real observatory. This is just an idea of what you can do if you do a physics degree, experimental physics, mathematical physics, or physics and astrophysics. And this is taken from an Institute of Physics booklet where they asked physicists working in Ireland to describe a day in their life. And these are I just cut out the headings. And so just to give you an example of the job titles that all these people had, and these were in Ireland, so it's not international, it's not in other countries. These are real jobs that physics graduates had in Ireland. And the Institute of Physics, www.iop.org, will give a lot of information about those. So you can see the huge range of really exciting careers that you can have if you study any of these physics degrees. I will just mention lastly about the science education option. So again, it's sort of like our single honours or double honours structures, but this is if you come in and you know you want to be a teacher. You do 4 subjects in first year, then 3, then 3, then 3, because you keep on education each year. And you have to do another 5th year, sort of a graduate year in the education department, and then you'll be qualified to teach physics in secondary school. So that's if you come in, you already know that you'd like to be a secondary school teacher. Experimental physics is one of the options that you do as part of that. So I say, my name is Crea O'Sullivan. My email address is at the bottom of the slide there, and I'd be very happy to answer questions today, or if you think of them at any other time. Say if you get back to normal, you'd be very welcome to come in and visit us in the department. Until then, I'd be very happy to answer any questions you have about experimental physics or physics with astrophysics. So I'll hand over to Peter now, who'll talk about the second department in the science faculty that does physics.
Okay, thanks, Crea. I've been answering questions in the Q&A as you went along, but I couldn't answer them all, so there's still.
I'll take a look.
I'm just going to get my screen up here and show you that. Now, hopefully you can now see my screen. So I'm going to take you through the Department of Theoretical Physics, what we do. And I think the first thing to say is don't be confused if I interchange the phrases theoretical physics and mathematical physics. For historical reasons, we were originally the Department of Mathematical Physics, but we changed. That was because a long time ago, the current department was actually essentially part of mathematics. And now we're a standalone department called Theoretical Physics. We use those words interchangeably, I think, so it's probably a good idea to not focus on the distinction between those. The department is the Department of Theoretical Physics. The course that we teach within MH201 is called Mathematical Physics for historical reasons. Okay, so it's just a bit of terminology there. We use them interchangeably. So there's been some questions already in the chat about this. So I thought I'd just say a little bit about what theoretical physics or mathematical physics is that obviously we work on the theoretical side of physics. Unlike experimental physics, we don't do laboratory work. Kriya mentioned that experimental physics is like the first year anyways, kind of starts from where you might have done physics at school, although you don't have to have done physics at school to enter that subject. The entry level for mathematical physics in our course is actually rather similar in some respects to the Leaving Certificate Applied Maths. So it's theoretical work which is predominantly mathematical in nature. So it has a stronger mathematical emphasis, more on figuring out the laws, the mathematical rules by which the universe seems to work, and less on actually making measurements and observations. So there's a distinction there. But I have to say actually that physics is not cleanly divided into theory, experiment. The physics is the interplay between those two things. So if you study theoretical physics, mathematical physics, and experimental physics together, you'll find that the whole is bigger than the sum of the parts. So they actually reinforce each other. So theorists, experimentalists make measurements or observations and find out, kind of how the universe behaves. Theorists try and work out why it's like that and not like something else, and why make predictions for experimentalists to measure. The fun part of the universe, the fun part of this is partly predicting what should happen on the basis of what we have inferred from other observations. And something that other theorists do is to actually work out what things could be like if the laws of physics were slightly different. So what would an alternative kind of universe look like? Now in Maynooth, I've just listed here some of the research areas that we are in. Quantum physics is a big area for us, and that's broadly interpreted. More recently, quantum technology, quantum computing. If I were to highlight two research areas that have been big in the last few years, it's quantum computing. We're actually part of a big national network of companies and another university that is researching into development essentially of software for quantum computers. That's going to be a huge thing in the next decade. Every government around the world is pouring a lot of money into quantum technology. So this is a very big area for us. We also work on particle physics theory. So making predictions of things to be measured, including the muon dipole moment, which was in the news just a few weeks ago, as somebody said in the chat. Another area is gravitation and cosmology. That's actually my area, cosmology. I work on the large-scale structure of the universe. And it's important to mention that Maynooth is the only university in Ireland that is involved in one of the most important cosmology space missions for the next few years, which is a European mission called Euclid, which is going to be launched in the next year or two. So the quantum technology and cosmology are big focuses for us, but we do a whole load of other things. And graduates with a theoretical physics background do all kinds of different things. It can be very general, meteorology and climate modeling, anything that involves mathematical modeling or anything like that, computational modeling, chaos theory. We have people going to work in financial modeling using things that they've learned in physics, but also other areas like superconductivity, materials, any area where there's some kind of development of a technology or a method that requires theoretical input. So it's really difficult to pin down where people go with theoretical physics, because it's really, really very flexible applications. You might learn how to use computational methods studying quantum mechanics, but those same computational techniques can be used in a whole load of other areas as well. So it's basically no limit to where you could end up with a degree in theoretical physics. Let me just run through very, very quickly what you would study here. So the first year, this is as it fits in the general science degree that Kriya has talked about. So in the first year, we start with things which are very close to what is in the applied maths leaving cert, although you don't have to have done the applied maths, and it doesn't matter if you have done the applied maths. If you have done it, we go well beyond applied maths. If you haven't done it, then we start at the beginning. So it doesn't matter, but it's just whether you've done it or not, but it does, it gives you some idea of the content. However, we do put in some special relativity in the first semester and some modern physics, by which I mean a little bit of quantum theory in the second semester. So that's all theoretical. We don't have labs in any year, apart from computational labs later on. So the delivery of this is through lectures and small group tutorials and problem-based learning. So that's the way that we work. It's kind of a similar style to the experimental physics, except we don't have the labs. In the second year, we move on. We teach a little bit of mathematics for those mathematical methods for physics, as well as some mainstream physics subjects. The mathematical methods strand you'll see carries on. So we teach some maths for physicists, which is outside what is taught in the maths department, and it's specifically for physics things. So we have electricity and magnetism. Third year, we do a lot of quantum mechanics. There's also some classical mechanics and so on, advanced courses in special relativity. And then the final year, you name it, we've got it. I mentioned a little bit about research earlier on and what we do in research. And I think it's important to say that this is a research-led curriculum, and students, for example, who end up doing single honors at the end, specializing in theoretical physics, do a research project, which is in one of the areas in which we're doing research in the department. And we're continually updating these, especially the advanced courses, in the light of new theoretical things that come out. So this is extremely important that you realize that there's a very strong link between theory, but between education and research in the university department. Okay, so that's just Newton's law of gravitation. Illustrate that's the kind of thing we do in the first year, mathematical physics. And then here's a little movie showing an amazing device, which is actually a superfluid fountain. So this is basically liquid helium that's heated by a tiny little light bulb at the bottom of this, but it essentially carries on forever, because a superfluid has no viscosity. It's no friction between the fluid and then the pipe or the nozzle, and it just so keeps it circulating forever. This is an actual movie, and as a theorist, what you want to do is to try and figure out why that happens. Actually, if you have a cup of superfluid, if you stir it with a teaspoon, it never stops. There's no friction between the superfluid and the side of the cup, so just carry on going round forever, unlike a cup of tea. So what we do is try and understand that, and in fact, the way you understand these things is using this kind of equation here, which is the nonlinear Schrödinger equation, quantum mechanics. It's this is also known as the Gross-Petievsky equation. So that's where you would end up in the fourth year. So I had Newtonian mechanics in the first year, very complicated quantum theory in the final year, and a lot in between. Where would you end up with a degree in theoretical physics, or including theoretical physics? Well, over past history, it depends a little bit on what you do, how you incorporate theoretical physics. As a rough guide, almost half, more than 40% of graduates actually will go on to do further degrees, masters, PhDs. Quite a number go on to do teaching. I think Kriya has emphasized the Institute of Physics and becoming a physics teacher. With a mathematical physics component, you can actually also teach applied maths at schools as well. So that's basically, we make sure that our curriculum has the requirements for teaching applied mathematics. But any area, and I've listed a few of them here, that involves mathematical modeling. It could be physics application like medical physics or bioscience. Biophysics is a big area these days. Nanotechnology, or it could be financial services and other things like that. It's really any kind of physics degree actually opens a lot of doors. Contrary to what you might think physics is very, very specialized. Well, you have to learn specialized things, but the application of physics is actually very, very general. So whether you do experiment or theory, you could end up in a huge range of different fields. Your only problem with a physics degree will actually be deciding where you want to go with it. It's really different from a degree like dentistry or something, where you qualify with dentistry, you become a dentist, that's your route. If it's physics, you can do anything, essentially. Not quite anything, perhaps, but there's a very wide range of possibilities. Okay, so Kriya's already mentioned general science, so I'll go very quickly through this. The main route for students to do theoretical physics, mathematical physics at Maynooth is through MH201, our omnibus or general science degree. And so what I've done here is just, you've seen these before, that I've just replaced mathematical physics, replaced experimental physics with mathematical physics here. I should say mathematical physics is the name given to the set of modules that comprise the course inside MH201, right? So we call them, they're all called MP something because it's mathematical physics. That's historical. Okay? So you do 4 subjects in the first year, 3 in the second, and then 2 in the third year, and then either 2 or 1 in the final year. So that would be a single major. And roughly half of the students who take mathematical physics to the final year actually do a final, a single honours within MH201, roughly half. So, and some students, of course, just do it in the first year, which is fine, and some just do it to the second year and then take their other 2 subjects on. It's very, very flexible. You don't have to decide at the outset where you're going to go. All right, so that's MH201. You can combine experimental physics and mathematical physics in this, and many students do, either just in the first year or through the second year or through the third year. But you don't have to. You can do either subject separately if you want to. I personally would recommend, if you're interested in physics, do both, certainly for the first year, and then decide, because I think they do, as I was saying before, that the whole is greater than the sum of the parts. It's a good idea that these two reinforce each other when you learn them. So I think if you're interested in physics, taking physics on in some way, then I would recommend doing both at least for the start. Okay, now we do have a denominated program outside of MH201, and that's called Theoretical Physics and Mathematics. And that, oops, let's go back to where I was. That's called MH206, and that's a completely different entry method. That is, oh, actually, I should have said that the typical CAO points for getting into general science, the general entry level for all the science subjects, it's around about 350 points. It's been that level for quite a number of years now. So it's actually 360 last year, but that's where you're talking about. And that's the requirement in maths. So that's for MH201. You'll see MH206 has actually a much higher entry level. It's over 500. It hovers around 500. And you have to have at least an H2 in maths for this. So higher maths is needed. This is a BSc, but it's also, it's 3 years. The standard general science BSc is a 4-year program. So this is a fast track program that essentially starts in the second year. So the first year students in this course, which we call TP&M for short, actually they bypass the first year and go straight into 2 subjects. So the flowchart for this one is very easy. It's 3 years and you do 50-50 theoretical physics and mathematics. It's a specially designed theoretical physics course. and a specially designed maths course to complement it. And it's joint honours, or a double major, if you like. And I've called it theoretical physics here because it's not the same strand as is inside MH201, which is the MPs. Right? So that's a much simpler structure. If you're absolutely sure you want to do theoretical physics and maths, you fast track and you concentrate on the two subjects right from the start. Okay, so now just to confuse things a little bit more, as if it were needed, there's now a way that you can do this course within MH201, and that's only come in the last couple of years. So this is a good route for students who are not sure they want to do theoretical physics and maths, perhaps, to start with, or who don't get of 500-ish CAO points to get onto this course straight away. So if you just look at those 6 blocks there, and then look at how you do this through MH201, you do the first year of MH201, you do math phys, because it's inside MH201, with 2 other subjects, perhaps experimental physics and another one, and maths. Everyone has to do maths. And then if you get high enough marks in math phys and maths, and I mean a first class mark, over 70% in the exams in these 2 subjects, you essentially go to this. So year 2 of your general science degree is 2 subjects instead of 3, and you go romping off and just do essentially what is the same course as MH206, but it's a 4-year program with this kind of preliminary year for you to go through before you concentrate. And these last 3 years are identical to the MH206 program. So people often ask me, should I apply for MH201 and do math physics that way, or should I go for TP&M? I think the advice that I would give is very, very clear. If in doubt, just go for general science, because if you're sure you want to do it and you do well enough, you can just go straight and you can change in year 2 to this. And this is actually popular. We get as many students doing this combination of theoretical physics and mathematics through MH201 as we do coming straight into the MH206. Okay. Now, another weird thing is, I don't mean it's weird, I don't think it is weird, but another thing that you can do here is to do mathematical physics through arts. So we actually have, as you may know, the general omnibus arts program in Maynooth is extremely popular. In fact, it's one of the most popular, it may even be the most popular degree program in the country. I think that's right, actually. It's not exactly. Give me the okay for that.
Yeah, it's the top number. It's the #1 CEO course in the country. The total number of applicants, Peter. Yeah, you're right.
So, and that's obviously because you can do mathematical physics through because it's a minor option. You might think it's actually a bit strange to get an arts degree with mathematical physics in it, but I should, just in the interest of full disclosure, I'd say I spent a career working in theoretical physics, and I have a BA degree. So it's not that unusual, actually. So you can do, the general entry standard into arts is 300 and something CAO points. It's a little bit lower than science. You still have to have done a science subject to get into that. And you might say, well, why would you want to do that? You could do general science and choose 4 science subjects in the first year. Well, the point is that you might want to take mathematical physics with a non-science subject, and many students do, and you can't do that within the general science, MH201. We have a number of students who want to do, say, theoretical physics, mathematical physics with philosophy. Another popular combination is music technology, which is offered in the general arts program. The connection between physics and music production is extremely close and goes back thousands of years. The ancient Greeks knew all about this. So we do get a number of students who do an arts program, which is between, which includes some element of mathematical physics. The one thing is that you can't do, well, the BA double major goes like this. Let's just say that 4 subjects in the first year, but these 2 will be art subjects. And you can do critical skills in the first year. It's a special subject for that. And then it's a 3-year program for a BA. And then you go down to 2 subjects, and then you can do a double major, which is 50-50 in the final year, or something you can't do in general science, do a major minor combination. So you do 2/3, 1/3 in that. We do not offer a full single honours mathematical physics in the arts program. There's just not enough modules to do that and not enough demand. But we do have people doing a major minor. And you can do other subjects that are sciencey through arts, including computer science, geography, and so on. So the combinations, there are lots of combinations within general science, but there are even more combinations within arts. And I can't possibly go through them all, but you can look at the general arts literature and you'll see how many possibilities there are. So this is, we don't get a huge number of students doing this, but we do get applications. There's several students per year who do mathematical physics through the arts program, and they end up with very interesting mixtures of. As Kriya has already mentioned, we can actually, you can include anything, any degree that we offer that is based on roughly the MH201 structure, which most of our science degrees are, can have mathematical physics as part of it. So biotechnology, physics with astrophysics, Kriya has mentioned, chemistry, pharmaceutical chemistry, there's all kinds of biological degrees where students do mathematical physics, at least for 1 year. And we really recommend that. It's mathematical physics in the first year of any science program is like balancing the mathematics, which you have to take, which is taught by mathematicians and is kind of has a pure maths emphasis, with the more practical applications of maths to mechanics and other things which we do in mathematical physics. And it's more the applications of mathematical methods there. And I think that's another example where the whole is bigger than the sum of the parts. If you do math physics with mathematics, then that actually helps you learn the mathematics as well as learning the physics. So I think, you know, if I was a physics student, prospective physics student, I would be thinking at the first year of doing, I mean, you have to do maths, but doing maths phys to help you both with the mathematics, but also with the experimental physics, which you should do as well. You might ask what the 4th subject is usually for people doing mathematical physics, and it's not always, I mean, people choose whatever they like really for the 4th subject, but it's often computer science for mathematical physics people, but not always. I mean, we have people do biology, chemistry, all kinds of other things. So it really is very flexible. Let me just say at the end here that I did a general science degree like the one here, not at this university, but like the one here. And my best subject at school was chemistry. And I went into what was called a natural sciences program, fully intending to do chemistry for the whole degree program, specializing in chemistry. But I had to do 4 subjects in the first year. Physics was one of them. And at the end of the first year, I decided that the physics was much more interesting than the chemistry turned out to be for me. So I ended up specializing in the second year. I did double physics and maths. And then my final year was theoretical physics. Now, the joy of the general science program is that it gives you that flexibility that you might come in and say, well, actually, chemistry is not quite what I like, or, you know, biology is not quite what I expected it to be. And you have enough other choices that you can take those through. So my general advice is, if you've got any doubt at all, then you can't really go wrong with MH201. My last item here is just, I was talking a little bit about the summer research projects, about the importance of research for our teaching. And I thought I'd mention this because it's actually quite a good place to stop, is that Maynooth offers summer undergraduate research studentships. So you can actually do a research project in a department or in a partner institution. during the summer. It's usually between the summer before your final year of an undergraduate program, usually, but doesn't have to be that. So there's a university-wide scheme called SPUR, which allows you to do this. You can look that up on Google that, and you'll see a lot of information about SPUR. The Department of Theoretical Physics also funds extra ones. We put 4 SPUR projects in every year, and they always get selected. And there's too much demand for those projects, so we actually make extra ones. So we fund our own. Actually, SPUR only funds 6 weeks of research. So what we typically do is increase these to 10 weeks for the SPUR one. So you can really get your teeth into something over 10 weeks in the summer. And we fund some extra ones which are not SPUR but just funded by the department. These are really good if you're actually thinking about doing research afterwards. You get some real experience of doing research, and it's a lot of fun. And I should emphasize that these are paid. You don't get a fortune for doing them, but it's the standard SPUR fellowship studentship is €1,500 for 6 weeks. If you multiply that by 10 over 6, the 10 weeks is €2,500. That's not a huge amount of money. It's €250 a week, but it's actually, it's a stipend, not a salary, so it's tax-free. So it's not so bad, actually. You do get actually paid for doing that. And I think these are a real, really useful for that roughly half of our students who are thinking about doing research afterwards. And that's it for me. I'm going to stop there. And we have a few minutes left, I think. Are there any questions in the chat, Ita, that we could answer?
There are, Peter. Thank you very much. There are questions in the chat box that possibly you might want to answer. I could, but it mightn't give them actually factual correct information. So I'd appreciate if you'd look at them.
So I'll go from that. So I'll read them out as I go through them, right? Because not everybody's staring at the chat. The last one there, did the SPUR go ahead last summer? Yes, it did. Although obviously they weren't allowed, the students on them weren't on campus. They were actually, we had to arrange computational projects that the students could do remotely, but they did go ahead and the students carried on. So I hope that answers that one. There's
another one there, Peter. If I do physics with astrophysics, can I choose to have mathematical physics to be more present in my studies?
Well, yes, you could. Well, I would personally recommend, if you do physics with astrophysics, that you do mathematical physics, certainly in the first year, because there's a slot for that within physics with astrophysics. It looks very similar to MH201 in the first year of that program. And you can also do, and actually, it's probably worth saying that some of our programs also, most of our programs allow you to slightly vary your collection of modules. So for example, when I talked about TP and M, it's 50-50. Actually, you could do a little bit more maths and a little bit less physics, or vice versa if you wanted to. So you can do a little bit more. I would recommend doing math phys certainly for the first year and then seeing how it goes. And then you can include it as you go on further.
Yeah, maybe I could answer that as well. So you could actually keep a strong component. So you could take physical astrophysics and mathematical physics as 2 of your subjects in first year. You could keep them as your two of your subjects in second year and third year. So you'd be 50-50 physical astrophysics and mathematical physics. And then in your final year, where you would in theory be fully physics astrophysics, we also give you a choice of modules within that. So there are astrophysics modules you'd have to take, but there's always a few modules that we let students choose. Because people have slightly different interests, and there are a couple of mathematical physics modules in general relativity and so on that we would, recommend you do. So you could actually keep on some mathematical physics. You could keep 50-50 right to third year and actually keep some in your final year as well. So yes, you could, if that's where your interest lies, you can keep a strong component in the physics and astrophysics.
Yeah, it's actually worth saying perhaps that we have not all the astrophysicists in Maynooth are actually in experimental physics. There are also some in math phys. So we have a natural kind of bit of an overlap. So we can offer more theoretical course modules in that are relevant to the astrophysics program, perhaps, whereas many students are more interested in the observational and instrumentation side, but you can pick and mix quite a lot as you go through the program.
Okay, I have another couple from Curtis. If you study MPH 602 and carry physics to the end, are you less qualified than doing just physics in your final year? So that'll be computer science with physics. So
less, I don't, less qualified, that kind of means less qualified. The question is what less qualified for what, right? So you could certainly with that mixture go and do anything that involves physics with a computational element, of which there's a lot of things these days. So it would have 50% physics if you did that, rather than 100% physics in your final year, but you'd have a lot more computational knowledge. And there are many areas of physics which are crying out for computational experts. So that mixture is a bit specialized, but there are plenty of opportunities for degrees with that mixture of things. And I'd say it's not unusual for our general science math phys students to carry on computer science to the final year, for example, and do joint honors that way. The MH602 is different, it's actually more software based, but that's definitely a combination of skills which is in demand. Yes, you can take it through to the end, but it will, you will be doing a little bit less physics than somebody who did a single honors, but a little bit, well, quite a lot more computation. So it swings and roundabouts, really.
Okay. Another one, is a superfluid not a perpetual motion machine if it doesn't stop?
So the answer is no. You notice that little fountain thing that I showed you is actually heated. So there's energy being put into it. A tiny amount is all that's needed. But imagine a cup of liquid. If you stir the cup of liquid and it keeps going round, that will just carry on. The body continues in a state of rest or uniform, so that's Newtonian mechanics there. But if you tried to take energy out to operate another machine, it would stop. So it's not perpetual motion, it's just the absence of friction. Things stop because of friction. But if there's no friction, then things just carry on going. But as soon as you try and take energy out of them, they stop. So they're not perpetual motion devices. Okay.
I'll take your word for that one, Peter. And
if they were, we'd all be billionaires by now. There'd be no need for energy. Actually, another example is superconductivity, for example. That's a wire. You can make a superconducting wire with no electrical resistance. CERN works on superconducting wires. The Large Hadron Collider has magnets made of superconductors. So there's no electrical resistance. So that huge magnet that goes around the CERN collider device dissipates no power. The current just runs without any losses. Unfortunately, it has to run at a very low temperature, and the fridges needed to keep it at that low temperature need about half the power output of the city of Geneva. So it does need energy, but superconductors and superfluids are actually real things, and they can be realized. They look really spectacular, but if you think about them, they don't actually violate any energy conservation or anything like that.
Okay, last question that I can see, Peter and Freya, and apologies if I'm not pronouncing this right. What is the muon result, M-U-O-N?
Yeah, so that was a thing that was in the news very recently, was it? A couple of weeks ago, which is that there's a particle, a fundamental particle called the muon, which is kind of related to a much more familiar particle, the electron. It's actually a heavier and unstable version of the electron with a negative charge. And because it's got charge and it's spinning, it acts like a little magnet, and it creates a dipole, what's called a dipole moment, which you can measure. So it likes to line up with a magnetic field. And people have, it's quite hard to measure for muons because they're unstable. But there's an experiment just went ahead recently and reported results a few weeks ago, which basically says that this dipole moment, which is the effect of the spinning charge, is actually not the same as what the theorists think it should be. And so there's two problems with that. One is that it's really difficult to measure this thing. And the other is that from a theoretical side, it's really difficult to predict what it should be, because you have to, in quantum theory, there are all these kind of virtual particles that contribute to the dipole moment. So there's now a big row between theorists and experimentalists about whether the theory is right and whether the experiment shows that the theory is in, whether the theoretical calculations are right, but the overall theory might be missing something. And a lot of theorists who actually think that they're not actually calculating the answer correctly. So they're not, so the real answer could be consistent with the experimental result. And there are others who think the experimental result might be wrong.
Who's winning, Peter?
Oh, experimentalists. Oh, right.
Well, our departmental expert is Jonivar Skullerud, who's a particle physicist, and he's involved in these. And he says, and I trust him on this, that actually the theoretical calculations, the contribution to the electric dipole moment from hadrons, which is heavy particles, it's not known how to calculate that properly. So the theoretical prediction is much more uncertain than people like to believe. So I actually believe the experimental result is accurate, but I think the theory is too hard to calculate what the answer should be.
Some of our attendees, if they come and become some of your students, Priya and Peter, might in a few years help with that calculation.
Yeah, and I think the exciting thing is it's not just we want to get this number and you know it a little bit, but not exactly. If it isn't what the theory predicts, it could mean that there are particles out there that we don't know about yet. We have this very successful standard model of particle physics, and we've never found an experiment that has disagreed with it. But that's happened before in physics, where there's just a small little nagging thing that, okay, we haven't quite tied up, and by trying to tie it up, we've suddenly found a new world, like quantum mechanics, the world of the very small, where we just didn't know about it. Or even only 20 years ago, certainly after I left college, this dark energy. So we now know the universe is accelerating. The expansion of the universe is getting faster and faster. And with gravity usually pulls things in. And we didn't know about that. And it seems that almost 70% of the universe now is made of this stuff called dark energy, and we don't know what it is. So I think it's really exciting for physics students that we're not just tying up a few loose ends, that there really is a lot of things out there, very fundamental, that we don't understand yet. And there's an awful lot of work to be done.
Yeah.
So Curtis has put a question in, if I can answer the last one.
Yeah.
They use supercomputers. Yeah, the point is, Priya said that, even within the standard model of particle physics, it's quite hard to calculate what should happen because it's a complicated theory, the standard model. So they do use supercomputers, and the technique used to make these calculations involves what's called lattice computations. And even with the biggest supercomputers in the world, they have limited capacity to calculate what should happen. So the question is basically, is it the standard model, but we're not able to calculate it accurately enough, or is the standard model missing something which would make the difference? And currently, we don't know. But that's the fascination of working in a subject like physics, where a lot of things happen very quickly. Like in particle physics and cosmology especially, things change very much. Cosmology as a subject is way different from what it was 10 or 20 years ago. And very often, the correct answer to a question when you're giving a public talk on physics is we don't know. And that's the case about the muon at the moment. And that's why it's exciting. We don't know. Let's find out. Mm-hmm. And that's what motivates scientists to study subjects like this. We really don't know the answer. Any of the possible explanations could turn out to be right.
It sounds very interesting, Peter and Priya. And if we have whetted the appetites of our attendees, just to let you know that the Q&A has just gone live at 1 o'clock on the Open Day platform, and very excited that Maynooth University academics such as Peter and Priya and students will be available to answer your questions. So please jump on there and start asking. And we hoped everyone really enjoyed our Physics at MU talk today. And if anyone has requests any information after that, please feel to get in contact with the admissions office or the physics departments themselves. And I'll hand it over to yourself, Peter and Creagh, to wrap it up.
Okay.
So I'd just like to thank everybody, sorry, Peter, for your attention. And just to emphasize again that we'd be very happy to speak to you at any stage if you've got any individual questions. You can look up the departmental web pages, and email us might be the easiest. And we'd be very happy to answer any questions that you may have. Thank you.
Yeah, let me just endorse what Creagh said. Thank you for joining in, and thanks for all the great questions as well. Some really interesting questions there. Don't be shy about contacting us. I know there's a 2-hour slot coming up where you can ask questions online, and we'll do the best we can to answer. Don't be frightened to contact us at other times. There's a general rule. If you get an academic, a professor or a researcher of any kind in physics, they will not be reluctant to talk about physics to you. And it excites us. So don't think it's some kind of imposition if you ask us a question about physics or how to study physics and so on. It's actually a delight to be able to engage with people who are interested enough to ask questions about it. So by all means, make use of the next couple of hours if you can, but any time other than that, you can easily get us through the web pages and so on. And we look forward to hearing from you. And I think that's enough for now, but we look forward to hearing from some of you in the future.
Okay, thank you. Bye-bye.